Assalamualaikum warahmatullahi wabarakatuh, everybody, and very good morning.
Good morning, doctor. How are you?
All right, okay, so okay, so just for some reminder, so our test 2 will be next week, which is on 30th December. So this is on Thursday. Okay, and what will be covered is actually up to this week material, half of it. So basically, it will be on. You should know about impulse response. You should know about a difference equation, system function, which is a H-ZAC, and then a DTFT, H omega. How to do the DTFT. Okay, and this week we will continue on DTFT. So, but the title is actually DTFT properties. So we will look at on this one. So what is actually properties? Right. So previously in Z transform, so we have also Z transform properties. So what actually we did is actually Z transform properties is helping us on how to solve the Z transform formulation. And this is actually the same. So we have some properties that can help us on how to solve a DTFT. Okay, so let's do some as usual. We do some recap first, so that everybody will get the idea of what actually we are trying to cover this week. Okay, so actually this is the whole thing of our course, which is a digital signal processing. This is actually digital signal processing 1. So we have another one. We have advanced digital signal processing. Okay, so if you are interested, you can take that course, advanced, maybe next semester. So actually what we are dealing with is actually on a system. So it is a discrete time system. And we are very specified on LTI system, a linear and time invariant. So this is the system that we are interested in. And we are covering what we call a filtering process, because the LTI system can be on other implementation, but we are covering the filtering. So what we have seen in this previously is actually first thing. So we have looked at what is a signal, discrete time signal. So how to get discrete time signal? So we do sampling. Right. So very important parameter is the frequency sampling. Okay. So with this frequency sampling, we do sampling. So then we get this discrete time signal. So that discrete time signal is actually how do we know? Because the time index is actually on n. So it's not on a t. T is a continuous time in second, and n is just a sample. So doing that, so we know that a system is actually doing something to the input. So you will get your output, a discrete time signal output, right? And to do that, to do something on the input, so you need to have the filter. Okay, you need to have the filter. So here is the process. To do the process, you need the filter, right? And that filter is, we have what we call an impulse response. So it is represented by impulse response. A filter or a system, the LTI system, can be represented by impulse response. Or actually, generally, we are actually representing the system, the LTI system, based on difference equation. If it is not LTI system, so that equation representing the system is not difference equation. We doesn't call it difference equation. Only if it is LTI system, then we represent it as a difference equation. And we can also represent it using impulse response. So this is only for unique for LTI system only. All right, and then we have seen what is what we call a filter coefficient. So there's two types of filter coefficient A and B. Right, so filter coefficient A is actually the multiplier, the weights for output sequence. And filter coefficient B is the weight or multiplier for output for the input sequence. Okay, A is for the output, B is for the input sequence. And we have covered because in time domain, so we have seen this thing on how to do it. So either you solve difference equation or you do convolution. Okay. having your input, having your filter. So either you solve difference equation or do convolution, you will get your outputs. So then that one is depending on the system. If it is FIR, you can do convolution. If it is IIR, you cannot do convolution. Okay, you need to use the difference equation only. And most parts of our course is actually covering on analysis. So we have seen this type of analysis, checking on stability and causality. Okay, and then so we also do a Z transform, checking stability and causality also. Okay, so we do this kind of analysis. And this is on chapter 4. This is week 4. We have done on how to do a Z transform, how to do an inverse Z transform using a table. So we have a table. So we have two types of table. One is just a Z transform pair table. The other one is a Z transform properties. So we are going to look at DTFT properties today. So we have seen that in Z transform last time. Okay. And so we have done that, and then in this, I think these several weeks, so we have covered on spectral analysis, which is on frequency domain. So how we need, why do we need this frequency domain? Because we have the purpose is different on each of the signal. So if it is an input signal, so this is the reason, because we want to identify frequency of the noise. And output, so we need to do some checking, either the output is correct or not correct. And then for the filter, okay, so this is the three things: input, output, filter. So we also do spectral analysis on the filter, so that we will understand what will the filter do. Okay, so we need to do that. But we didn't do the analysis yet, whether this is a good filter or not a good filter. What we have covered so far is just on how to do a transform. So specifically the DTFT, discrete time Fourier transform. In continuous time, we have last time, so we have a Fourier transform without the name of a discrete time because it is a continuous time. And we have also actually a Fourier series. Okay, last time for continuous time. So you have covered Fourier series and Fourier transform. And we're not going to go deep on that, on those transform. What we're going to cover in detail in this course is what we call a discrete time Fourier transform, and later discrete Fourier transform. Okay, two types of Fourier transform. So this is we already know that. So we have if we do DTFT, so we should have a magnitude and phase. Okay, because originally after you do DTFT, you should have a real and imaginary value. But those real and imaginary value separately doesn't give us much information. So we need to convert that real and imaginary values into magnitude and phase. Okay, so this is what we have done. So we have seen one example on FIR system and one example on IIR system last week. And we will see more example today, right? So what else? So that's what we have covered so far. And this week we will do more examples on the properties, and then we will cover this one also. So the relationship between DTFT and Z transform, exactly. And then later, so we will do DFT. So this is later, DFT. And then the rest of the course will actually discuss on how to design a filter. Okay, so we need to understand the process first, and then we need to do analysis after we understand the filter using the analysis. So then it is time to design it. Okay, so that will be the last. So we have two types of designs. So one is for FIR, another one is for IIR system. Okay, so any questions so far? So before we start our new chapter today?
Not any updates or concerns regarding the assignment that you want to tell us?
The assignment is, okay, let's see. Oops, my internet is not very good. Okay, for the assignment, generally, what should you do? What should you have now is is actually every group should already put your visual notes on the Jamboard. Okay, so make sure you have done that. So if not, please do that as soon as possible. Okay, I didn't check the Jamboard yet. Okay, so because maybe I will check it by today or tomorrow. So, but hopefully every group has posted or has put your visual notes, the compile visual notes of 5 topics, okay, into one single page and put it on Jamboard. Okay, do you have any concern on, do you have any difficulties on doing that? Anyone of you? So maybe some members is missing. Do you have any problems? Anyone?
That means we have to use the reference you gave us, Doctor, for the missing members.
Yes, you just use that one. Okay,
All right.
so you just use that one. And for those who are missing, so please, please participate in the forum. Okay, even though you are late, so please participate in the forum, because if you don't participate in the forum, and your friends already taking notes from somewhere else, so means that high possibility you will get 0 for your assignment. Okay, that will not be good. And this week you should do some discussion also. But that discussion can be on online, like online meeting. Maybe you can do it on WhatsApp. So whatever it is, but you need to show some proof of discussion. And in that discussion, I need to see that everybody is actually taking part. Okay. So if you do a meeting, but you just keep quiet on the meeting, so didn't much give any ideas or some input, so you won't got any marks also. Okay, so this is where you need to participate. And actually it's not that difficult, because assignment, you have a lot of time to do it, right? This is not test or exam, which is the time is very, for test you just have 1 hour, for exam you just have some maybe 2 hours and 30 minutes to do it. So assignment is very easy to score, right? So it is very easy to score. It's a waste if you ignore it. And again, I'm going to remind everybody that this is not assignment that you can take something from your friend and then copy and then submit. You're not going to be able to do that. Okay, because you need to participate in a forum, in a discussion. Okay, you need to show your involvement. So there's nothing to submit. There's nothing to submit. So just as a group, you need to put your visual notes in the Jamboard. The only thing that you submit is only for the first part, which is you submit the visual notes. So the rest needs your active involvement. Okay, and if you involve in the forum, in the discussion, so it should be easy to score the marks. Okay, doctor, if some of the group mate is missing, we can use other people's note who is in other group. Yes, sure. I already share a link, right? So you have all the notes, right? So you can use any of the notes. You can use any of the notes, right? You doesn't have to wait for your team member. Okay, so we need so that this learning process is moving. So we doesn't want that if someone doesn't supposed to give us his input, so but he's missing, so we cannot move. So just use any of the notes that I share. Okay, and actually it is those notes is actually from all of you. Okay, those who submit. All right. Yes, unfortunately, actually, this semester, what I have to tell you is I never faced this kind of a problem. 2 or 3 students didn't submit. That's normal. Okay, that's normal. 2, 3 students didn't participate to the forum. That's quite normal. But this semester, not sure what's happening. So there's a lot of you didn't participate and didn't submit.
Why do you think it is that like this, Doctor?
I'm not sure. Maybe everybody already maybe tired on online learning. Maybe
Maybe
okay.
COVID? Was it?
Maybe COVID. I'm not sure because whatever the problem is, please let me know. Right, I'm here to help all of you. Okay. So whoever actually message me personally, normally I will reply as soon as possible. Okay. So he doesn't want any one of you actually left behind. But if you didn't tell me what is the problem, so I'm not sure how to help. Okay, I'm not sure how to help. So help me to help you. Right? I'm sure there are many problems. Even your problem is just laziness. So that's also a problem. That's a big problem. So maybe if after you talk with me, so you can reduce that kind of problem. I'm sure there's a lot of problem there. So especially this semester, because I never faced this kind of this kind of response from students. So normally just 2, 3, at most maybe 5% didn't do it. So that's, as I said, it's quite normal, but this is not normal. This semester is a bit strange.
Quite the phenomenon, yeah.
Right? That's I think it's very strange. And no worry, actually, it's not too late. It's not too late. If you have any problem, just let me know. So if I can help, I will help. All right. So you just need to come forward and discuss. And we should discuss. We should discuss. All right. Because especially on the assignment, you should actually assignment in total is a 20%. That one is supposed to be a very easy marks to score. So, but if you don't score assignment, then it will be a bit more difficult to score in test and exam. Right? Okay, so hopefully, and those who didn't yet to submit, I still open for submission. I still open for submission, and I still open the forum so you can do the discussion. So please continue doing that, and then please continue on this week. Okay, so and hopefully those who didn't participate listen to this video. Okay, because maybe those who are in this live class, maybe you won't have any problems. So those who have a problem is actually maybe didn't even participate in this live class. So hopefully you guys listen to this class offline, right? Okay, so let's continue to our class. So which is this week, we will cover what we call a discrete time Fourier transform properties. So what is that? So this is actually the table. So you have seen this table, this kind of table before for Z transform. Okay, so it is almost the same because DTFT is actually just a subset of a Z transform. So actually what we do here is just we change the notation so that it becomes a DTFT. So because what we have is for DTFT, Z is actually equals to E j omega. Okay, so we just change that. So actually we have seen this, but in terms of Z, not in terms of omega. So now we are going to look at it in terms of omega. Okay, so what is the important properties that which is typically we will use it. So mostly is the linear property, the time shifting. This one is quite rare, so you're not going to look at this much. Time reversal, yes. So sometimes we look at it, but it's not as most of the time you're going to look at linear, time shifting, convolution. Okay, so these three. So these are common properties that we're going to use. Okay, and these are also what we call maybe a popular question in test and exam about the linearity, time shifting, and convolution. Differentiation is quite rare. This one sometimes we do this. Multiplication is also quite rare. Okay, I think I haven't seen any question on multiplication. Even on if we do assignment and everything, so it's quite rare that we are using this property, because most of it, so we're going to dealing with convolution. And this one, this is very important. So linearity is quite basic, so we can avoid this one. Okay, so those three things. So what is the time shifting? Time shifting is if you have your vector system or signal delayed. Okay, so actually we can have the one which is not delayed multiply with e to the power of minus j omega nd. So previously we have seen this as a z minus n of h z nd, right? So actually this is the same, because we just change z equals to e j omega. So we have seen this. Okay, let's look. So this is the one that which is quite similar to the previous, which is on z transform. And this is new. This is new on DTFT because actually DTFT is asymmetric. So DTFT is actually symmetry. So why it is asymmetry? Because it involves this e minus j omega n, involve cos and sine. And cos and sine is actually symmetry. Okay. So if we have this one, h omega, what is a h omega? H omega is actually h n e minus j omega n. And we can expand this into cos and sine, such this. So actually, what is the real part? So the real part is actually just this part, which is hn cos. Okay, and what is the imaginary? It is actually multiplied to the sine signal. So we can separate that. And since this cos omega n is actually equals to, this is actually some trigonometry basic formula. Cos omega n is actually equals to cos minus omega n. Okay, this is not this DSP, this is a trigonometry. And sine omega n is actually equals to minus sine minus omega n. Okay, so how do you get this thing? It is from those, okay, so you have your, how about, what is the sign of cos here? What is the sign of cos here? What is the sign of a sine here? Sine here. And previously in maths, you already learned also for tangent. Okay, cos, sine, and tangent. Okay, so every quarter of this, so you should know what is the sign. So actually, this is basically, it is we have this. So then from this, so we know that the h real is actually equals to h real. It is the same if it is a positive omega or negative omega. Okay. So actually, this is the positive omega. And this is the part where you have a negative omega. So if you do the cos, you will have the same value. Okay, you will have the same value. Okay, and then so this is actually a real and imaginary is not really our. We're not interested in real and imaginary, as we have learned from last week. The one that we are interested is on the magnitude and phase. Okay. So because of this symmetricity of cos and sine, and we know that h real is based on cos, and then imaginary is based on sine. So then we know that our magnitude supposed to be this h omega, the positive omega, and the negative omega. The magnitude supposed to be the same, right? So we call this even. So let's see what will be the shape after this. And phase on positive omega and negative omega, it is on an opposite. It has an opposite sign, and that shape we call it odd. Okay, this is like we can call it evenly symmetrical. This is oddly symmetrical. So what will be the conclusion is, so then we should have this is a correct shape of a frequency response. Correct shapes. So this is real. So real must be, so this is what we call an even shape. So why? Because this is a 0. Okay, as a recap, so which plot is this? Is this a full plot? Is this a shifted plot, or is this a half plot? So which one?
It's a full plot.
Full plot? Are you sure?
Yeah, very confident.
So we have 3: full plot, shifted plot, and half plot. Half plot is, of course, is not a half plot. And actually, this is a shifted plot. Okay, a full plot, it starts with 0. The 0 is now at center. So this is what we call a shifted plot. Full plot, you should start 0 and then end at 2 pi. Okay, so this is actually the full plot, or the whole plot, or we can call it the original plot. And this is a shifted. So if you plot this one, you should get something like this. Okay, this is what we call a full plot, and this is actually a shifted plot. All right, so whatever it is, actually, it is enough to observe half of the plot only. So that's why we have the third type of plotting. So we call it a half plot. So half plot is actually from 0 up to pi only. Okay, we take from 0 up to pi. So that will be enough for analysis and observation. All right. So, okay, this is but if we want to identify whether this is an even shape or it is an odd shape, so we need to shift it, because after we have a shifted plot, the 0 is at center. So now we can see that this is symmetry. The negative part, this is negative pi. All these are actually negative omega. This side is a negative omega. This is the positive omega. So the positive omega side and the negative omega side, the magnitude is the same. So if we look at here and here, so maybe this is omega 1. So this is actually minus omega 1. So the magnitude is the same. So this is what we call an even shape, or evenly symmetrical. So it is a symmetry, but it is a symmetry as an even shape. This is also symmetrical, this one, but this is H imaginary. So this is the imaginary part. It is this is oddly symmetrical. Okay, so why we call this oddly symmetrical, and this is even? Because this one, example, this is at pi, the positive side of the omega, and this is the negative side of the omega. So the y-axis, okay, the y-axis, which is the phase. The y-axis is the phase value. So the phase value is actually on opposite sign. If this pi is the value is alpha, at negative pi, the value is a negative alpha. So that's what we call an odd shape. Okay. So so this is where for magnitude. So the first one is this one is actually for real part. This is imaginary part. So this is example of magnitude. So magnitude is supposed to be even shape, and this is a phase. Phase supposed to be odd shape. Okay, or the opposite sign. This is the same sign. Okay, so that's why when we have if you have a real plot, so you shouldn't have this kind of plot. So this is an example of a wrong plotting, because this is not even shape. For real plot, you should have an even shape. And this one is an imaginary. Imaginary, you should have a odd shape. This is not odd shape. This is even shape. Okay, so it's not possible that we have an imaginary plot to have an even shape. So this is not odd shape. Odd shape is supposed to be if you have something over there. So it should be something like this. Okay, from here and then continue, because we should have a negative sign for omega and negative omega. Then the imaginary part will be correct. So if not, it's not correct. And this is a magnitude. So from minus pi to pi, so we can see that this is not even shape. So then this is a wrong plotting. And this is also a wrong plotting for phase, because phase is supposed to be odd. This is even. Okay. Is the phase plot called an odd symmetrical shape, doctor? Yes. So we call that. For phase, we call it odd symmetrical. And so that's why this is wrong, because this is actually even. So be careful when you do the plotting. As a hint, you will need to plot something on testing. Okay, there's a question on DTFT, so you should plot something. So one of these, it can be real, it can be imaginary, it can be magnitude, it can be phase. Okay, so it will be one of it. You need to plot. All right, so symmetrical properties more. This is how we actually summarize what we have seen on the previous slides. So any real signal, if you have any real signal, or actually any real system is a Hn. This is a Xn. Okay, so either it is a Xn or Hn. And it is real. Real means because our signal normally we doesn't have an imaginary signal. Okay, because practically we don't have that. When you record any signal, so you will get a real values. It doesn't get a complex value. So, but because this is on the theoretical part, so we need to write this. So any real signal or system. So this is actually the one that we have seen on the previous slides. So this is a summary. Do you need to memorize this? No need to memorize this, because this table will be given in test 2 and exam. Okay, you just need to know how to use it. Right? So no need to memorize. And so this is new. So if your signal or your system, okay, is an even signal. So we have seen what is the even. Even is, so this is an example of even at 0. So the negative index and the positive index will have the same amplitude or magnitude. So that is actually even. And this one, so if we have even signal or system, right? So which is the xn is actually equals to x minus n. So how do you say this? The amplitude for the positive index is actually equals to the amplitude of the negative index. So then we can use this formula, because if you have an even signal, your DTFT, so what is this? So this is your DTFT. Your DTFT is actually equals to just a real part. So there is no imaginary part. Okay, and this is quite interesting. So even actually when we do design later, so we will make sure that we will have this symmetricity, because it makes things easier. Okay, so we will have a real value only. We doesn't have an imaginary value if it is even signal. We will see some one example. What is the original formula? Original formula, x omega is actually equal to summation of if you use x, this is xn, e minus j omega n. Okay, so n is actually from minus infinity up to infinity. So you need to do that. And this is actually a simplified equation. Original is this one. So we can simplify it. For symmetry signal. So that's why we learn these properties so that we can simplify our solution. When we are solving to get a solution, so we have a simplified equation. Okay, so instead of using this E minus J omega n, so it doesn't have to worry about this E minus J omega n, you just do cos. Because in this equation, so you will only see cos. So there's no E minus J omega n anymore. So that's why this one becomes easy. So what is this equation? Instead of the n from minus infinity up to infinity, so you just need to do it from n equals to 1 up to infinity. But then you need to multiply by 2 and then plus with the x 0. So we'll see one example of this later. If your signal or system is odd signal, so let's see, this is an example of even signal. Let's say you have at 0, this is n, this is 1. Let's say you have this is 2 at n equals to 1. So you should have another one here, which is equals to 2 also. So this is what we call even signal or system. Okay. So, but if you have odd, so you should have like this is, let's say, 0. This is a 1. This is minus 1. So if you have 1 here, so you should have negative 1 here. This is even. This is odd.
Excuse me, doctor. If I have on 1, if I have instead of negative 1, I have 2.
Which one, the even or the odd?
On the odd.
The odd. So you have 2.
I have 2 on the first
negative
index. 1? On the 1 index, n equals to 1.
Okay, so if you have 2 here, right?
On n equals to negative 1, I have katakanlah 1. So is that even? Is that still odd, or is it something else?
Is it such this one?
Yes, exactly.
This is not symmetric. Okay, this is not even. This is not odd because this is actually not symmetric. So what we are interested in is if you have a symmetry signal or system. Okay, because this is very unique. If you have a symmetry, then you will have this equation. If you doesn't have a symmetricity, you cannot simplify the equation. You need to use this original equation. Okay, so this is not symmetry.
Thank you, doctor. I thought this one is called odd as well. So thank
No.
you for clearing out.
Because if this is odd, so at negative 1, it should be minus 2. If you have 2 here, this one's supposed to be minus 2. Or if this is 1, this one's supposed to be minus 1. Such this one. So this is odd. Okay. So yes, actually this is quite good because we have a simplified equation. So that's why actually when designing, so most of a design filter, especially for FIR. So actually this properties is actually works on FIR. So it doesn't work for IIR. So IIR is a little bit complicated. FIR, so we can have this. So we will design it so that it will be symmetric, because everything else will be simplified. Even if all of you remember from a last content on a Z transform, so we have learned on what we call a realization. Okay, so how can we reduce number of memory and operation, the multiplication, the summation operation? We can reduce that if we have a symmetry signal. Okay, so that's why we are really interested in this symmetry signal. So we can reduce the number of operation and the memory. Even the calculation becomes simplified. So such this. Okay. So as much as possible, when we do design on FIR, so we will do this symmetry. So that's why we learn this property first. Okay, we need to understand what is actually symmetrical. So we will try to avoid FIR filter, which is not symmetric. Okay, because we have a lot of advantage when we have a symmetry signal. Okay, so let's see. I think we have time to see one example. So that's why if we look at example, so this is example 1. So this is a symmetry FIR, and then example 2, a delayed symmetry FIR. Okay, still FIR. Example 3. So this is a odd FIR. This is example 4. Example 4. This is some convolution. Still, if you look at the HN, so this is FIR. Okay, we don't do any example here on IIR because symmetricity actually doesn't really works on IIR, because IIR is how many samples do we have? We have an infinite number of samples, so it is really not possible to get a symmetricity. Okay, so quite difficult to achieve that. So that's why most of the it really works on FIR. And on a discrete time system and signal, so normally even another ones, we normally try to avoid IIR. As much as possible, we will design FIR. So unless we have a strong reason, so we do IIR. Okay, so okay, let's see. This is the first example. What is the question? The question is find H omega. So this is again, you need to know each one of these notation. So what is this called? This is called frequency response. The original. Okay, it doesn't have an absolute value. This one is called magnitude response. See, original, we call it frequency response. If we have that modulus, so we call it magnitude response. So this is actually the one that we are interested in for our analysis and observation. Okay, not this one. This one is phase response. So this is another one that we are interested in when we do analysis and observation later. And this is just another one. So because sometimes when we do analysis, so we need to rescale our y-axis. So this is magnitude dB. Okay, so we will see some example later. So why we need to do dB instead of just a magnitude, we need to rescale. So this is actually just rescaling y-axis, for observation. So not for calculation. Calculation we will use this one. Okay, so this 3, 1, 2, 3. Okay, so we have Hn. We will need to do this H omega, the magnitude, phase, and dB for our impulse response, which is described as 2 delta n plus 2 plus 2 delta n minus 2. And if you put it on vector, it should look like this. Okay, and this is evenly odd. Evenly symmetrical. Okay, because this is n equals to 0. So this is the center. And then we have at n equals to 1, it is a 0. At n equals to minus 1, the negative index is a 0, the same. N equals to 1, this is 2. And this is the same, which is equals to 2. So that's why we call this evenly symmetrical. Okay, so Hn is real and even. So now we know that this is evenly symmetrical. So it is n, every value is actually real. And of course, we're not going to do a complex time domain signal. Okay, so actually you can just ignore this real because we're going to use all real value in time domain. So Hn is actually even, thus, so this is where we can do this equation. Originally, what is the original equation? H omega is actually equals to summation of n minus infinity up to infinity of Hn e minus j omega n. So then, if we do this, so this is actually checking from minus infinity up to infinity, but what we have is actually from minus 2 up to 2. So what you need is actually just h minus 2 e minus j omega times minus 2 plus h2, because this is the next sample that has a value. The rest is actually 0. Okay, then this is just multiply with e minus j omega times 2. This is what we do originally. Previously, we used this equation, and we can have h minus 2 is 2, h2 is 2, so this is 2 e minus j becomes positive, 2 omega plus 2 e minus j 2 omega. Okay, so what's next that we do for this equation? So we can do this, and from the trigonometry equation, the Euler's formula, even the Euler's formula doesn't have to memorize, so it will be given in test and exam. Okay, so what is this? So this is actually equals to 2 cos 2 omega. Finally, you will get 4 cos 2 omega. Okay, so from last week, so this is how we solve the DTFT using this equation. But because we already know that this is actually evenly symmetrical, so we can use this equation instead of this one. So instead of this one. So by doing this, so we just take h0 plus 2 multiply of a summation n from 1 up to infinity hn cos omega n. And h0 is 0, so this is h0, 0 plus 2, so you take 2 that one. And then the next n, which we have a value, amplitude other than a 0, is at n equals to 2. So this one. So this is 2 here, replace this 2, and then cos omega multiplied by 2 because the n is 2. So then you get 4 cos 2 omega. So you can solve it either using this equation or you can solve it using this equation, right? Because we know that this is evenly symmetrical. Okay, so what's next? So then we need to find the magnitude. So this is what we call frequency response, because this is just a h omega, original h omega. 4 cos 2 omega, because we already know that if it is even, so what we will have is just a real value. So what is the imaginary value? 0. Okay, so this is the real value only. So then actually doing the magnitude is very easy, because actually what is the magnitude? Magnitude is a real squared plus imaginary square root. Because we doesn't have an imaginary, you just put a absolute value. So whatever the value here, so it will give you, it will convert it into a positive value. Positive becomes positive, negative becomes positive, right? Absolute value. And this is the phase. The phase, we have seen this before. If the imaginary is 0, so this is actually the results. Okay, this one is already fixed. This one's already fixed. Okay, we doesn't want to deal with the hassle of the maths doing this, solving this. So we just take that, okay, if the imaginary is a 0, so this is the output, right? So, but of course, if you are interested on how to get this thing, so you can go to these notes, the last one. So this is how you can get that output, that result. Okay, from this tangent inverse slide. Okay, you can go there, and then find out, so how do we get this one? And dB is just whatever the magnitude that you have, multiply with 20 log 10. So there's no plot. Okay, let's plot, at least for the first one. So this is the magnitude, because in test 2, you need to plot something. So let's plot this one before our break. So now we have h omega equals to the magnitude of h omega equals to 4 cos 2 omega. So when you do a plotting, so it's up to you. So you can do a plotting on a full plot. You can do a plotting on a shifted plot. You can do a plotting on a half plot. Okay, you can choose either one. So any of the three. So let's do half plot. So now let's do half plot. So what is a half plot? So you should have omega from 0 up to pi. So this is the one that you should have. And this is actually quite easy to plot. Quite easy to plot because this is just a cos signal, cos to omega. So for if let's say this is let's do the h omega first without having the magnitude. So this is just h omega is actually 4 cos 2 omega. 4 cos 2 omega. When the omega is 0, this is actually 4 cos 0. 4 cos 0 is actually equals to 4. Okay. At pi, if this is pi, so this becomes a 2 pi. Cos 2 pi is again 1 multiplied by 4. So you get 4. And at pi over 2, so if we have a pi over 2 here, so then multiply by 2, so it becomes pi. So then pi, cos pi is a minus 1. Minus 1 multiplied by 4. So you get minus 4. Okay, and then you have something here, you have something here. So this is a pi over 4. So if you do a pi over 4 here, so it will be a pi over 2. Pi over 2, cos pi over 2 is a 0. So actually this is because we know what is the shape of a cos. So actually the whole plot. So this is h omega. So it has a positive value on y-axis and it has a negative value on y-axis. And then to have a half plot on magnitude response, so what should you do is just make everything. This is pi over 4, 3 pi over 4. This is 4. This is another 4. This is another 4. And this is a 0. This is a 0. So that will be your magnitude. Okay. All right. So last question before we start, before we take a break. So what do you think? Is this a band stop, band pass, low pass, high pass? So which one? So what is this? Low pass? Okay. Any other answer? Other than low pass? Can we say this is low pass? So what is a low pass? Low pass is passing the low frequency and then we will remove the higher frequency. So it's not very accurate because actually we do pass some of the higher frequency. So these are actually higher frequency, these are higher frequency. So we did pass through the lower frequency, but we actually also do pass some higher frequency. So low pass frequency, low pass filter is not really accurate. So what else? Of course, not high pass. Band stop. Yes, we can say that this is actually a band stop. So, but it stopped at 2 frequency. So one is at pi over 4, another one is at 3 pi over 4. So this band stop is actually having two frequency, which is which the filter stop. Okay, so these are two frequency, exactly these two frequency, because this is actually 0 and this is actually 0. So we remove this frequency, we totally remove this frequency, right? And actually this one has a name. So actually this filter, we call it comb filter. In Malay, we call it sikat. Okay, because it looks like a sikat. Okay, it looks like a comb. So there's a name for it. So very simple filter, it has a name. When it has a name, means that it is very significant. Okay, simple, symmetrical, but significant. Okay. Okay, so we take a break. So we will start again our next session. I will give you a new link. So we'll start at 12:10. All right, so you guys again at 12:10.